just go through the sign conventions. Number one, it says if you're traveling around the loop from negative to the positive side of a terminal, that is going to be a positive EMF, a positive voltage, okay? So if I'm traveling around from negative to positive, I pass it this way from negative to positive, that's going to be a positive voltage, okay? So I add that, okay? If I travel around the opposite way from positive to negative, I have to subtract that 10 volts. Okay, so that's 2 rules. Rule number 3, if I said the current is going this direction, right, and I'm also counting around the loop in that direction, that is going to be a minus IR. Okay, so in other words, and this will make more sense in a little bit, but if I'm like starting here at this junction and I'm going around, I add my 10 volts, I come here, now I'm going down here, and the direction I decided to travel around that loop is the same direction as the current, then that's going to be a minus voltage, or a minus IR, because remember, voltage is equal to IR, right? Okay. If it's the opposite direction, like let's say I arbitrarily choose to go this direction, okay? All right, and I get over here, and now the direction I'm going is opposite the direction I set for the current, that's a positive voltage. So we're adding that I times R. All right. I fully am aware that right now you're like, what the hell is he talking about? It's okay. It's okay to feel that way right now because you haven't seen it in action, and I'm about to put it in action right now. All right, so loop laws. I am deciding to go clockwise around this loop. I'm going to pick this loop first. Could I pick this loop first? Totally. Could I pick the outside loop? Totally. But I'm picking this one because it's simple and easy. Okay? So let's start there. I'm going to go around this loop, and I could pick clockwise or counterclockwise. Totally arbitrary. You might want to just pick one constantly, so let's go clockwise. Let's say we'll always go clockwise. And you want to start at one point and then end at one point. And around that whole loop, delta V has to be 0. All right, so let's apply our conventions. So I'm going to start here, and I'm going to start marching. March. Oh, I get to a battery. Am I going negative to positive or positive to negative? Oh, I'm going negative to positive, right? Lovely. That means I add this 10 volts. So this is going to be plus 10 volts. Okay? All right, good. Keep marching. March. Oh, I get to a resistor, right? Do I want to add IR or do I want to subtract IR? Okay, well, I'm marching in the same direction that I set the current. That must mean I subtract it. So that means minus 30 I3. Why 30 I3? Well, this is resistance, this is current, so the voltage drop at that resistor is I times R from Ohm's law. Remember, delta V equals IR. So the delta V here, the voltage drop, the amount of voltage dropped off at that resistor to supply its energy so that that light bulb or whatever it is can light up is going to be I times R, or 30 I3. All right, march. Oh, I'm back to where I began. That means that must be 0. You guys see what we did? I summed the voltages around this loop, and I got 0. Whew. Okay, that's one of our voltages. And remember, we want to find the I's through all the resistors. So now let's go to this loop. Let's pick this loop because we need I2. I2 is important, okay? Because that's the current through this resistor. So let's do the same thing, all right? I am going to start marching, and I'm going to start here. I'm going to go around, and I'm going to come back to here, okay? So let's do it. I start here. March. Oh, I get to a resistor. What do? Well, if I'm going in the same direction that I set for the current, it's going to be a minus sign. So that's minus 20 I2. Okay? I march. Oh, I get to a battery. Cool, right? So what do? I'm going positive to negative. That means I subtract it. If you're going through a battery, positive to negative, remember, positive terminal is always the bigger one. Positive is the bigger one. I get here, so that's going to be minus 5 volts, okay? And I march, get to my junction, march. Oh, check it out. I see that I got to another resistor. So here, I'm going opposite the direction that I set for the current. I set the current's this way. I'm going opposite. I have to add this 30I3. So there's going to be plus 30I3 equals 0. Okay. Wonderful people. We have 1, 2, 3 equations and 3 unknowns. We might be able to solve for our answer here. Okay. I'm going to take this v out. You don't really need the unit there. It just kind of complicates things. Don't think it's a variable. Okay. That was just the voltage unit of 10. But this equation, I just want to point out, is beautiful because it only has one variable, right? That makes it so easy to find what I3 is. That means that, so if we have 10 minus 30 I3 equals 0, then that means 30 I3 equals negative 10. Negative, right? Negative, subtract negative. They both become positive. Divide both sides by 30, right? I3 is just equal to 1/3 amps, or 0.33 amps, right? We now have the current through that resistor. How cool is that? From these 2 simple laws, very, very smart physics people from the 19th century figured out what the current through there must be. Okay. All right. Well, check it out. All we got to do is substitution now. If we put this I3 in for this I3, we should easily get I2. So let's go for it. So we have, I'm going to separate this. So we have negative 20 I2 minus 5 plus 30 times 1/3 equals 0. Okay. I then am going to just multiply that. So it's minus 5 plus 30 times 1/3 is just 10. Okay. Then that's equal to 0. Okay. And run out of space. Run out of space here. I'm going to erase this up here to make a little bit of room for myself. Okay. So that would mean that 20 I2, minus 20, minus. I'm adding these together. That's going to give me plus 5. Right? Okay. Getting there, getting there. So we have minus 20 I2 equals negative 5. I'm just bringing this over there. 2 negatives, they cancel out. Divide by 20. Divide by 20. I get that I2 equals 1/4, or 0.25 amps. Is that what I get? Oh, yeah, that's what I get. Okay, so we have our 2 answers. I2 is 0.25 amps. I3 is 0.33 amps. We know the current through each resistor. Now, the problem didn't ask for it, but we could also easily solve for I1 now because it's just I3 plus I2. Pretty cool, pretty cool. There's a lot of math on here. I encourage you to stop at this video and go through this problem again on your own so that you feel comfortable and know why I did each step. Okay? I hope I was clear in explaining why I did each step. And I also want to point out one other thing. I2 and I3 are both positive. That means that I was really lucky and picked the right directions of these currents right off the bat. Okay? If I2, let's say that for I2 I got negative 1/4, all that would mean is that really it's going in this direction. Okay? But that's not the case here. It's really going in this direction because I'm a genius and I picked it right just from the beginning.